Okay, so this is my rate of change FRQ problem. Yes, let's get to it. So this is some background on my problem. Danny runs the 400-meter race each week for a meet. The fastest I've ever finished the race was in 52.88 seconds. Using the video footage I'm going to show you right now, I was able to find my splits at every 100 meters, which I was then able to find my velocity by simply dividing the amount of time by the total amount of meters. So let's say, for example, at 13.22 seconds, I was at 100 meters, and to find the velocity, I just divide 100 meters divided by 13.22 seconds to get that velocity of 7.56 meters per second. And I use this formula to complete the rest of my data. Okay, so now I'm going to be showing you guys some video footage of me running the 400 meters. So right here, Alfredo had just passed me the baton in this 4x4 relay, and I'm running, and around right here at the 100 meters, I clocked myself at 13.22 seconds. And then for the rest of my data, at the next mark, I clocked myself in at around right here 26.48 seconds, and this is almost right here near the 250, and I'm approaching the 300 right here. And right here I clocked myself in at 39.78 seconds. And as I finish up, my split was a 52.88. So this is me running the 400 meters, and this is what helped me find my data for the table. Okay, so here's my data, and on the X value we have our time in seconds, and on our Y I have meters per second, which is M of T. And at 0 seconds I'm traveling at 0 meters, and at 13.22 seconds, like I said earlier, I found my meters per second, my velocity, by dividing 100 divided by 13.22, and that gave me 7.56 meters per second. And the next one, 22.48, I found that by doing 200 divided by 26.48, and that gave me 7.54, and so on. So this is my table, and this is just, and on the bottom is just like a little diagram of the track, just to get like a reference of what the track looks like in case you've never seen it. Okay, so this is my actual problem. The problem states, Danny runs a track meet every week on a 400-meter track. Each week, Danny competes in the 400-meter race and can finish the race in 52.88 seconds. Danny's velocity is given by the function of v. The value via t, where t is measured in seconds and via t is measured in meters per second, are given on the table above. And part A is basically asking, use the data from the table and find the approximate rate at which Danny is running at time equals 35 seconds. Okay, so like I said, I'm going to be using the data from the table to find the approximate rate at which Danny is running at time equals 35 seconds. So first off, where it says v prime of 35, that's what I'm going to be entering, and I'm trying to find the slope or the velocity of how fast I'm traveling. And so I use the slope formula, which is y2 minus sub 1 over x2 minus x1. So it would be, and 35, I'm gonna use points that are above it and below it. So that would be the point of v 39.78 minus the point of v 26.48 over 39.78 minus 26.48. And that would give me 7.52 minus 7.54 over 13.22. And the 7.52 minus 7.54 would equal 0.02, and divided by 13.22, that would give me a velocity of negative 0.0015 meters per second squared. Okay, so now on to part B, and part B is asking for evaluate the bounds of 0 to 26.48 via t dt, and use the correct units, and how does your answer compare to the context of the problem. Approximate the value of this formula using the Wright-Riemann sum with 4 intervals seen in the table above. Okay, so we're going to be using the Wright-Riemann sum, and like I said, we're going to be using the bounds from 0 to 26.48 seconds. And from 0 to 26.48 seconds, we're going to be using only these two for the Wright-Riemann sums. So first off, we have the 13.22, which was our starting time, and then that's going to be multiplied by the by v of t, which would be 7.56, and then that's going to be added to our sum of 26.48 minus 13.22, which would give us 13.26 times our v of 26.48, which would give us 7.54. And that is seen right here, 13.22 times 7.56 plus 13.26 times 7.44. And when we multiply them together and we add them together, we would get a total of 199.92 meters, which is approximately where we're supposed to be at, because at this time, at 26.48 seconds, I clocked myself in at around 200 meters, which is pretty close to this number. Okay, so now moving on to letter C, and letter C says Danny's velocity is modeled by the formula v of t equals 0.167 minus 0.00152x plus 0.00002835x squared. And t is measured in seconds and v of t is measured in meters per second. Find Danny's acceleration at t equals 15 seconds. And basically I got this formula from Google Sheets, just entering them in and finding a formula. Okay, so right here we have our formula that we got from our Google Sheets. And we are going to be inserting our t equals 15 seconds into our x's to find Danny's acceleration at 15 seconds. So right here we add 15 and 15, and when we multiply and add them all together and we simplify, we get 0.0027 meters per second squared. And this number basically means that basically my meters per second was pretty consistent with each other, and I wasn't really like changing. So yeah. Lastly, part D says, based on part C, find Danny's average change in velocity on the interval 0 is less than or greater than t less than or greater than 52.88. Okay, so the last problem we have is letter D, and once again we are finding Danny's average change in velocity on the intervals 0 to t to 52.88. So here's 0 to 52.88, and we're going to be integrating this whole formula that we had in the previous problem. And so when we integrate it, we separate them 3 times. And then when we simplify them, we get these 3 numbers right here. And then we simplify it even more. And then lastly, we multiply it by 1 over 52.88. And that'll give us our solution of 0.0029 meters per second. And that is Danny's average change in velocity. Thank you.